We're recording the meeting. I hope everyone's okay with that. Welcome everyone to the hub and the Cowichan Station Area Association, home of the Cowichan Station Area Association and the Koksilah Working Group. So we're so really pleased that you could make it tonight. Cindy? No. Okay. So. Yeah. People on Zoom. I'm looking here, but I have to. People on Zoom, thumbs up if you can hear everything okay. Yeah? Okay, good. Jill's happy now. So tonight I am so grateful that you all came. And I am very grateful that Cowichan Watershed Board is offering this evening of learning about science and the recommendation, the latest hot off the press stuff on the Koksilah. So there's lots of people working in the Koksilah and it's pretty exciting. And I would first like to acknowledge that we are on the traditional territory of the Cowichan people. And for that, I'm very grateful. They cared for the land for thousands of years and we've screwed it up. So we're here to talk about how we can hopefully fix it, I hope. So many of you know me. Many of you maybe don't know me. So I see new faces in the audience. My name's Alison Nicholson. Jill always says, oh, you wear lots of hats, but actually, Jill, I don't like wearing hats. I wear scarves. And one of the scarves I'm wearing tonight is I'm a member of the Koksilah Working Group. And another scarf I'm wearing is I'm also a member of the Cowichan Watershed Board. And hi, Sarah. And I am also head of IT tonight. So when things go wrong, we can all blame me. We have a great team, a Cowichan Watershed Board team. Jill has organized this. Jill does all the organizing. Jill, I don't know what the watershed would do without it, Jill. So, you know, big hand. Yeah. Our wonderful Tom Rutherford, who is stepping down shortly as the executive director of the Cowichan Watershed Board. So we're going to miss him, but he's going to stick around and help out, I think, afterwards. So. Yay. Tom's co-chairing with me tonight. So my job is to do the IT and the logistics and the housekeeping stuff. And then I'm going to turn it over to Tom. This is very high tech for us. I am standing here because this is where you stand so that you're up there. And so all the one speaker is on Zoom. Jeff is on Zoom. And we have an audience on Zoom and we have an audience at the hub watching the screen of Zoom names. Mostly names, a few people. And the presentations will be up on the screen and everyone should be able to see them. And the sound, I hope, is working. Just the one thing we ask is that all people on Zoom keep their mics off, muted. Jill will put you on mute if she catches you off. And if there are any issues, please chat in the chat box. And questions tonight, we thought we'd sort of level the playing field. So everyone, the agenda is such that we'll do one presentation, we'll take a 5-minute stretch break, and then another presentation, and then we'll do a questions at the end. And so if you could write your questions down, and I can actually maybe ask people just to pass these out. Yeah. Okay, good, thanks. Team effort here. So we'll do questions at the very end, and those questions that we don't have time to get to, we will answer and send around emails with the answers to the questions. So if you would like to get the answers to the questions, you need to make sure we have your email. And people on Zoom, of course, we have your email, but otherwise, please sign up with your email and we can make sure you get those. We have other people here tonight. We have the Twinned Watershed. There's lots more. It carries on, the Twinned Watershed study we're here to learn about tonight. If you'd like more information, I'm sorry, Angela? Melissa. Melissa's the fisheries biologist, right? Working on it. So she would love to talk to you about that. And this study here, Jennifer Shepherd is here, and Christina Disney are here. They're the Twinned Watershed, not the Twinned Water, the Xwulqw'selu Connections Project. And this is a really exciting new study that UVic is doing, a 5-year study about groundwater, surface water connections and community connections with the watershed and with each other, and how we can make changes to based on what we've learned. So that's going to be a really cool project, and you can learn more about it here. And if you're interested in getting involved in the community, helping us to do more outreach about what we've learned about the watershed and what we could do to change our land use practices, Koksilah Working Group sign up is right there on the front little table. And Sarah, and is Barry here? Barry, Sarah and Barry are Koksilah, and Barry's instrumental in helping us set up tonight. So thank you. And Todd and anyone else from Koksilah Working Group. Anyway, please join us. Oh, Scott, yeah, Scott's here. So, oh, Rick, we're all over the place. Okay, so we've done the high tech thing. We've done the mute. Oh, we'd appreciate masks, although there aren't as many people as we thought we might be crammed in here. So, but if you can bear with us and keep masks on when you can, when you're not eating or whatever, that would be appreciated. Help yourself to goodies and tea at the back. Washrooms are in the hall. There's one right across from us, and there are more down at the bottom of the stairs. Okay, fingers crossed this works well, everyone. I think I got it all. Did I, Tom? Okay, over to you.
We're going to stand at exactly the right spots. So thank you, everybody, for coming tonight and for joining us on Zoom. Watershed Board member and Cowichan Tribes Councillor Cindy Daniels sends her regrets tonight. She would say something like, "Siam not sie eats skakit tanakwel tuniat coats and toma." Just acknowledging that we are on the traditional territory of the Cowichan people, and it's a real privilege to be here, right? And it's a real privilege to be here with all of you. So we've got 3 great speakers tonight, so I don't want to step on their time, but I thought a little bit of background, like 3 minutes, might be helpful. So in 2021, the Watershed Board was able to access some funding that allowed us to retain some real subject matter experts to help us answer some questions that we think are going to be really helpful to our community as we work together to try and address some of the challenges, some of the water challenges that are associated with climate change, right? So those challenges are here, they're significant, they're not going away. And we believe that it's people like you, it's members of our community that are going to come together to address them, but we need the help and guidance from the scientific community, and we've got that in spades, and some of that is the story we'd like to share. So we've got 3 great speakers. Jeff Anderson is a fluvial geomorphologist, easy for me to say. Jeff is going to talk a little bit about the actual form of the river and the relationship between that and the water that flows through it and the fish that live in the water. So it's a really interesting subject, and Jeff is a world-class guy. He's worked all over Western North America, from Montana to Oregon, right up to the high Arctic. He's worked with the Chant team on the Columbia River, who have been doing like groundbreaking work for the last 20 years. And I think more importantly to us, Jeff is a great teacher, and he was able to work with our community to like build capacity so that we can start understanding and doing some of this work ourselves. So we're really, and he is in fact joining us from Smithers tonight. So great to have Jeff with us. Our other two speakers are people you may know. Heather Pritchard is a forester. She's worked in, I guess, as a policy analyst and a habitat specialist for the province. She was the community forester for the Harriet Proctor Community Forest, groundbreaking work in our province. And Chris Steger is a wildlife biologist with over 30 years of experience. Not saying Chris is old, but 30 years of experience across a wide variety of wildlife focused fields and activities, from developing and training people around wildlife tree assessment to integrated resource management planning, like a broad spectrum. And they're going to talk about the riparian health of the Koksilah, so the health of the vegetation on the sides of the river on the salmon bearing reaches. So we're really lucky to have three super qualified subject matter experts to share what they've learned about our river and our watershed with us tonight. So Jeff, I'm hoping you can somehow magically share your screen and turn on your microphone, and I'd like to hand the baton over to you. I can't believe it. This is actually working. Okay, thanks everybody. Really appreciate it. Okay, Jeff.
Thank you so much, Tom. First question is, are we seeing the right screen?
You bet. Looks good.
Okay, thank you. So as Tom mentioned, I'm a fluvial geomorphologist or river scientist, and I'm living in Smithers, British Columbia, the unceded territory of the Wet'suwet'en people. I did grow up in Vancouver Island and had the privilege of having a cabin at Shawnigan Lake and visiting the Koksilah. So it's really fulfilling to come back much later in my career and participate in some of the science that's happening there. And to Tom's point, it's a big team, and we're all just poking away at individual pieces. And so that's what I'm going to share tonight, is some of the pieces that I was part of poking away at. And if I can. So what we're going to do is just spend a little bit of time talking about habitat evaluation. And so there's three studies that we're talking about tonight that all came together. Second study is a desktop environmental flow assessment. We did a field-based environmental flow assessment as the third study. And then at the end, we'll just mention a couple of next steps and some things that can help this project on its trajectory forward, I guess you could say. Before we jump into the first study and we look at the habitat assessment or the habitat evaluation, I think it's important for us just to sort of step back to that 10,000 foot level and just think about what is it that makes a river or a watershed healthy. And this is a pretty simplistic diagram, but it's also very precise. And on the far left-hand side, we have what might be called watershed integrity. And we know this as really nice places to be in the forest. There's intact forest, there's forest of all ages, there's wildlife and wetlands and lakes and so on and so forth. And maybe a landscape without a lot of land use, you could say. On the other side of the spectrum is an impacted forest. And so it just has less watershed integrity. For us, and for thinking about the river, the really meaningful parts of that reside in the middle. And some of you might be busy reading what some of those are and kind of nodding your head and thinking, absolutely, this middle group of ecosystem functions are really what it takes to bring everything together for watershed health. And a quick glance to the top right corner there, and we see we have watershed integrity on the left, or the tall axis, and watershed health on the bottom axis. And whichever one of those starts trending to the right-hand side, or trending, away from healthy, we can see, where we get good functioning ecosystems on the top right in the green, and where we have harder, more impacted ecosystems. And that's really good thinking, right? As a community, you guys are coming together wondering, how can you participate? How can you contribute to something you feel passionate about? And, a river is simply the sum of its parts. And so this schematic is meant for us to think quite broadly about the watershed as a whole, as we start to dive into some of the river specific science. So when we started talking about how we were going to look at the river and what to assess, we wanted to cast a bit of a wide net and cast in a few different directions and to see, where we might get some bites and some nibbles, so to speak. And so what we decided is that we do a habitat assessment, and that's called Mesohabitat right here. And that's really looking at the condition of the physical habitat in the river. We also looked at what we called a tier 1 or a desktop environmental flow need assessment to really get an idea of the quantity of water, precipitation coming in, groundwater coming in. What is that that's really making up how much water is available in the river? And of that available water, the third study here is called a tier 2 environmental flow needs assessment. And that's really looking at, how available is that water? Is it the right speed? Is it too slow? Is it too fast? How is that working together with the habitat at large? And we felt that these 3 studies together were a good place. There'd be a few good casts, and we get a bit of an idea of what we're dealing with the lower Koksilah River. So I'm going to start with the Mesohabitat assessment. And what I'll do is I'll move through each one and provide some concluding remarks and then move on to the next one. And as Alison mentioned, if you guys do have questions, please write them down and happy to answer them at the end. So the Mesohabitat evaluation is meant to be a rapid assessment where a team of people walk up the river and collect a pile of really detailed information. They tap that into an iPad as they go. They take some pictures and measure some things. And overall, that data really gets distilled down into some analysis and some presentation. And so in the first thing we might get from that is a map like this. The fine details don't matter as much to everybody as the legend on the bottom left. And really what we're starting with is a spatially explicit map of where all the pools, riffles, runs, so on and so forth are, just to start to get an idea of the quantity of different types of habitat, how much pool habitat is available and how much riffle habitat is available. Pools are kind of like the couch where the fish like to hang out, and riffles are sort of like the fridge where all the food comes from. And so it's important that there's a good balance between the two. And this is a starting point of understanding that. What we realized really quickly from this work was that there was an awful lot of one type of habitat and not a lot of some other types of habitat. And this was our first indication that there were some signs and symptoms in the river, that there's some impacts and some broken parts or some problems that need some thinking. And what we can see from that, sorry, my bad, is that each of these arrows right here is pointing at something that we're saying is a deep glide. And I'll talk that through in a minute. And when we look at this other set of arrows, these are the natural glides that were there. And so we can see there's a really big difference between the impacted glides, these ones, and the natural glides, these ones. They're just outnumbered by 4 to 1. And by the numbers, what we see right here on this pie chart in yellow is the deep glides, and it's sort of the numbers are a little small, but the yellow represents 68% of the habitat we looked at. And the shallow glides are that light smurf kind of blue, representing only 4% of that habitat. And, we'll talk through this as we go on, but we realize that this is actually one of the bigger issues with habitat itself, not the watershed mechanisms, but just some of the issues, some of the symptoms in the lower watershed. So when we say an impacted glide, really what we mean is something like this, right? It's fairly flat, it's fairly slow, and it's not really behaving as it's supposed to behave. It admittedly is a very pretty spot and is quite endearing. But at the same time, it's the lack of complexity and the lack of structure that we're really keying in on when we're doing a habitat evaluation. And what I mean by that, if we look right here, on the bottom left, you'll notice there's a categorization of poor, moderate, and good. And this is a map of stream structure. And when we say structure, really what we mean is almost anything in the river that's having an interaction with the stream bed. So wood, boulders, root wads, bedrock that protrudes out into the river, kind of anything that gives the river some variation or some heterogeneity. And so we keep track of that and then start to calculate how much structure per 100 meters. And really science understands what's good for habitat and good for fish. And that's really what this classification shows, is that there's an awful lot of poor and moderate structure throughout the stream. And so really what that means is there's very little wood and very few root wads. There is a couple of large log jams, but there's very little wood other than that. And wood is good when it comes to fish and fish habitat. Another metric that we're sharing with you tonight is complexity. And complexity would be things like side channels or off-channel sloughs or eddies and pools that are over on the side of the river that otherwise might be flowing fast. You know, variation in the habitat, refugia for fish to hang out, places where predators might hide and dart out from. And overall, what we can see right here is an awful lot of the lower Koksilah River has poor complexity. And so, you know, there may have been older side channels back in time. There may have been off-channel habitat back in time that is just no longer there. And that's really what this map is showing. So if we were to come back to the deep glide here that we're calling impacted, oh, my bad. What I really want to key you guys in on, and sorry, I'm just looking for my laser pointer here. Really what I'd like to, whoops, that's not going to work at all. My bad. I touched the wrong button. Sorry, folks. I'll talk you through it. Really what I want to key us in on here is on the left-hand side of this image, we can see, you know, the bank is fairly steep. It comes straight down. The river is very flat, rectangular even, and it comes sort of up more or less fairly straight on the right-hand side. And if we think about a concrete flume, something that's made to move a lot of energy through that flume, it's a very similar shape to this. And the energy in the river is starting to dictate the shape of the river. And so it strips all the structure and the complexity out, sterilizes the habitat, if you will. Sterilizing as in removing the wood and removing the structure. These are some of the things that we started to notice really early on. And so some of the way that we package this information when we're thinking about the health of the stream and then, you know, the different parts or something we might call Geo Indicators or Riverscape Indicators. It's kind of fancy scientific language, but it's really just talking about, you know, the condition of the channel or the geomorphic condition of how it's moving around and where its evolutionary stage is. And this is more or less a report card. And really what we see here is of these 7 Riverscape indicators, most of them are in poor condition. And this is really, I think, intuitive for a lot of you guys in the river that used to know what the fish values were or how the river used to behave when you were kids and so on and so forth. And this is really the numbers, the science probably confirming some of your observations and intuitions around the river. Some of the reasons that we're seeing the shape and the health or the impacts the way they are has to do with the river evolution and how water is moving through it and how land use throughout the entire watershed is interacting with the river. And so we're not looking to digest this stream evolution model right here as much as just pay a little bit of attention to the shape of the river from one to the next. And what we see on the bottom right-hand side, if this was a clock, call it 5 o'clock, we have stage 4, and this really represented what a lot of the river was. And it's starting to incise down. It's taking a lot of energy. It has some erosional banks, and it's starting to lose some of the structure that once was in the river. Structure that you might see on the left-hand side at 9, 10, 11 o'clock with stages 7, 8, 9. And, you know, that's where the river is a much healthier form and offers a lot more ecology. And so science is really starting to key in on the difference or the presence of evolutionary stages to understand what's happening with ecology and why. And so that's one of the things that we looked at. At the same time, we wanted to know, you know, where's the energy, how much energy is here? It looks like it's really having an impact on the structure and the complexity, but we wanted to dive into the numbers a bit. So we did a peak flow analysis. And what we're looking at here is, we've all probably heard of the 1 in 100 year rain event or the 1 in 100 year river event. And so this is a chart of those types of frequencies. And on the left-hand side is the 1 in 500 year events for stream flow. And then to the right of it is the 200 year event. And all the way on the right-hand side is the 1 in 2 year event. You know, that moderate water that we're expecting to see every couple of years. Each one of them has 4 bars because these are the climate normal windows. And so Environment Canada packages data in 30-year windows so we can understand the trend or if there is a trend in the data. And so this is a really simple analysis, but again, it's an early fishing trip. We just wanted to chuck a couple of casts and get a line in the water and see what we're dealing with. And one of the things that we noticed right away is that the largest events, the 500s, the 200s, the 100s, seem to be trending downwards. And I forgot to mention this, but on the left-hand side, the white bar is 1960 to 1990 data. So a 30-year window representing stream flow during that time. To the right of it is 1970 to 2000. Again, 30-year window, just moved forward by 10 years. 1981 to 2010, and the dark one is 1990 to 2020, right? So our present day is this dark blue. And really what we noticed is these high flow events were presumably decreasing over time. Again, first analysis, simple analysis, but a pretty clear trend. At the same time, we looked at the lower flows, and what really intrigued us was particularly the 1 and 2 year event seems to be increasing in time. And really what this means is that water that comes into the watershed, call that rainfall, is moving through the watershed really quickly and potentially, right, is over time getting faster and faster. And so often linked to land use throughout the entire watershed, and it's how we're interacting. We think about that first graph that I showed with watershed integrity and watershed health, and where we are on that spectrum. And so this analysis is indicating that, yeah, water is moving across the landscape pretty quickly, and that's why the river is having some high flow or peak flow impacts with it. Overall, as we wrap up the Mesohabitat evaluation, what we know, or what we did, is we used Water Survey of Canada data for the peak flow analysis. So there was about 70 years of data there, Canadian climate normal windows. We did several standard analysis, I guess you could say, right? If there's any techies in the room, this is really common stuff. This is really rigorous stuff. It really can run with the dogs, but the details are probably unnecessary right here. And it's just that understanding that, you know, as those 2 year events increase, the energy with the 2 year event is where the stream has the most power. And so as we see an increase in that 2 year event, that really does describe why the structure and the complexity is starting to decrease over time, because that moment before the river spills its water is really where most of the energy is concentrated. And so it's concerning to a certain degree, but it also makes a lot of sense to see the 1 and 2 year event increasing given what we're seeing in the river. Okay, so in the interest of time, I'm just going to roll right through the 3 of these, and then we'll move on to the next presentation. So what I'm going to talk through now is a desktop study for environmental flow needs. And when I say environmental flow needs, everybody's mind goes in a different place. And so I'm just going to pause for a minute while we read this. Or in fact, maybe I'll read it out in case there's people in the room that can't read the front of the screen. So environmental flows describe the quantity, timing, and quality of water flows required to sustain freshwater and estuarine ecosystems and the human livelihoods and well-being that depends on these ecosystems. This came out at the World River Consortium in Brisbane, Australia in 2007. These are the words of 700 scientists, policymakers, governments from around the world coming together and realizing that we're losing our rivers, so we're losing the health and the biodiversity, and we really need to move forward on figuring out how to get them healthy again. So this next study, the desktop environmental flow needs assessment, is looking at both the quantity and the timing of flows in the lower Koksilah River. Again, using the same data set, Environment Canada, or Water Survey of Canada's data from the Koksilah. So this represents 70 years of data. And what we're looking right here is just a standard hydrograph, excuse me, of flow in the Koksilah River. And this red line right here is what's called the mean annual discharge. If you average all that number, all that data together the whole year, you get one number, and this flat line is that one number. And it basically says the mean annual discharge is 10 cubic meters per second. And we'll talk about that in a little bit. And so an environmental flow needs assessment is often trying to balance the needs of both people and nature. And so this graph, or this periodicity table right here, is the nature side of this. And on the left-hand side, we see different species of fish. Just to the right of that, we see different life stages of fish. And then all the colored X's and the months of the year indicate when different life stages of different species are using the river. And there's general understanding in science how much water is required in the river for different life stages. And that's really what this process is matching together the needs of the fish, the volumetric needs of water, if you will, the needs of the fish with how much water is actually in the river. Excuse me. So this is what that looks like once we sort of blend all this together and we do the analysis and we move some things around. What we're looking at right here is the first cut of what that analysis would say is needed in the river. And this blue line right here represents what we're calling a conservation flow, or the flow that would keep all the fish super happy in the river. Obviously, that line is really high at the moment, and that's just what we're going to talk about here. What we know in aquatic sciences is that 20% MAD, which is represented by this dotted line right here, is usually how much water we would like to see in the river most of the year, most of the time, for most of the species. A very general comment, but a guideline nonetheless. And so when we see a river has dipped way below this, we certainly want to drill deeper and understand what's driving that, so we can understand if it's natural or not. A caveat with this data set is it began in 1950, and there was an awful lot of work in the watershed prior to 1950, several different sectors throughout. And so it's really important to recognize that there was likely profound hydrological impacts in the watershed before this data set started. And so it's important not to jump to the conclusion that this is a natural flow, but to ask ourselves the question, is it likely natural or is it likely impacted? These lines right here represent the last 70 years of what we call the 7-day low flow. So the flows that persist for 7 straight days at a 10-year recurrence interval. So once every 10 years, how low does it get for a whole week? And that's a really informative number for fish because they're fairly resilient and they tend to bend and weave to their environment. And although there's not a direct correlation between fish and these numbers, it's really suggestive of what their hard line is, if you will. Before we sort of jump to some of the conclusions, similar to the peak flow analysis, we wanted to do a low flow analysis and just kind of drill into that question that I was just mentioning. Why is the water so low in the summertime? You guys all know that it's low, but was it always low? And somehow are the fish adapted to this, or is this a problem? And so we did a peak flow analysis, very similar. These 4 dates across the bottom are the same climate normal windows. We're just reporting the data on an annual basis here instead of one column for that whole climate normal window. And we see in the black dotted lines, this is the same type of trend line that we saw on the previous peak flow analysis. And so what I want to bring you guys' attention to right away is, we have general downward trends from April through October, right? So as we're getting into the lower flow months of the year, on average, over time, water is decreasing, available water is decreasing. We can see that May, July, and August have really abrupt or steep decreases in available water. You guys are from the watershed, you definitely have your own ideas and good ideas as to what's driving this. And I think what we want to stay open-minded to is it's never one thing. It's always a number of things that are coming together to push extreme outcomes as opposed to mild outcomes. The other thing to key in on is that it's not all going down in November and to a very minor degree in January. We also have some water going up. And I believe that this is the timing part of environmental flows. And so maybe as rain shifts further into the autumn and hits the top of the watersheds as rain rather than the top of the watershed as snow, as we're in that shoulder season of the year, this might be indicating that the shoulder season is actually shifting towards the winter. And as rain on snow events or rain on wet soil events happen late in the fall, we're seeing a general increase in those low flows, right? Again, we're just adding a bit of context to an otherwise fairly simple analysis. But, we're casting a few lines here and we just want to see what's happening in the watershed and start to put that bigger picture together, bring this information to you guys to stimulate some discussion and figure out how to move forward from there. So if I bring this back to this diagram, because I think this is really meaningful for how society perceives our interactions with rivers, we know that from 9 o'clock through 12 o'clock, those are really, really healthy forms for rivers. You know, 6 o'clock and 7 o'clock is not too bad. But when we are over here in the 3s, the 4s, and the 5s, we know we have problems. And we see those problems. The community tend to know the problems are there, the people that are paying attention. And this graphic right here does a really good job of describing how humans interact with rivers. And you'll notice this comes from the US Department of Agriculture. So this is a human problem everywhere as opposed to a Koksilah thing. But some really important information resides in this graph. And as we contain a river, and so I mentioned the 1 and 2 event, as we contain the water in a river with levees, with roads, with land use, we push the river together with bulldozers, we start to focus that stream energy inside the riverbanks instead of letting it spill over on the floodplains and release its energy. And as that river etches down, what goes with it is the water table. And so here they're calling this the fire hose effect, when we get this stream power just concentrated inside the river. And notice at the bottom, they're referring that channel incision and widening, increased stream power, results in minimal large woody debris, habitat complexity, and coarse substrates. And I think a lot of you might be nodding your heads with your own observations and knowledge of the river and realizing like, yeah, absolutely. That description seems on point for many places throughout the Koksilah, but not all of it. So bringing it back to some of the results from the desktop environmental flow assessment, that line was quite high above the red line, but really what we needed to do is come up with some practical and reasonable restoration goals. And so what we have right here as a suggestion for near-term restoration, and the how part is a big question, and that comes way later. But nonetheless, what makes a lot of sense is to try and lift the river up a little bit. And we can see with these 7Q10 low flows that it's actually pretty close to some of these places, right? That line's a little higher. But you know, we're sort of seeing that we can key in on this jump and try and increase that water a little bit up to 5% MAD. And we'll describe what that means in the next study here in the next couple of minutes. And as a longer term goal, it would be great to see that water get up to 10% MAD, because again, this 20% line is usually the ground floor, unless we got some really good science indicating why the river is able to function with less water in it. And that would probably be a circumstance where there was really good complexity and really good structure, and habitat was actually okay at low water. Probably not the case we're talking about in the lower Koksilah. Third study, to motor right along, was a field-based environmental flow needs assessment. And so same description of environmental flow needs that we mentioned at the beginning. But this time we're doing some really uber science inside the stream. This is really intensive work, a lot of hours, a lot of time on the stream for the crews that were out there doing the work. And this is called an incremental flow assessment because it uses the data, the flow measurements and surveying data of water levels. It uses it to model across a range of flows. So we can kind of model any flow level and ask the question of, you know, well, what is the habitat? This is a hydraulic habitat approach. This was a traditional hydraulic model that was built. And it focused on the lower Koksilah River from the highway bridge all upstream to about Camp Karina. And within that stretch, what we were doing is we're sort of focusing 5 different assessments within the field-based work. We're looking at coho fry rearing, steelhead fried rearing, insect production in riffles, Chinook passage through riffles, and deposition of fine sediment in those impacted deep glides that we pointed out. At the same time, we're considering the previous results that we've mentioned here as we're starting to synthesize the conclusions of this study together. And we're using those to sort of talk about, you know, what is next and where can restoration efforts be focused. All in, whole of watershed thinking is really what the Cowichan Watershed Board, and presumably, I don't speak for them, but I'm assuming the Cowichan Tribes is also supporting whole of watershed thinking. And really what we mean when we say that is everything is connected. A river is the sum of its parts. And so if we want to manage the river, we do have to manage at the watershed scale or with whole of watershed thinking or recommendations. So the way that this particular work was done, this is not hiking up the river and collecting information. That we chose 17 locations for stream transects. And each of those was surveyed with a really high resolution survey of the transect itself. And then a whole bunch of stream flow measurements and velocity measurements and substrate measurements happen along the way to populate the model and sort of get at the type of information that talks about fish use and how the fish like to utilize that. So the graph on the top left is not meant to be understood in full. It's just meant to give you guys a bit of a glimmer of what modeling habitat might look like. And so right here, if we see the river with some water in it and the riverbanks up here, each of these levels, each of these lines corresponds to a color above it. And really what it's showing is at super high flow, the green is the habitat that's available, and it's actually only usable habitat on the edge of the river because it's really high flow. And at the other end of the spectrum, at really low flow, so this dark blue line is right here, that dark blue line. So at this exact flow level right here, the usable habitat is actually more towards the center of the river because those flows, those substrates are hospitable. And that's really what this process is about, is looking across a range of flows to find out what is hospitable and what is not, and then rolling that into those 5 studies that I just mentioned. And so with the 5 studies, they each had their own results. And starting at the top, insect production in riffles, that really wants to see 10 to 60% MAD, or 1 to 6 cubic meters per second in the river. Often in the August, it's down at 1% MAD. And so this particular model or this particular result is indicating 10% MAD to 60. So really big jump. Steelhead fry, 0.25 to 0.7 seem to be the bottom floor, if you will. And these results, it's worth knowing, is kind of the bottom floor for where each of these species or components could flourish. This isn't meant to be the actual deadline where things are critical past this. These numbers are meant to indicate river health. So siltation, when the river is greater than less than 0.3 cubic meters per second, there's a high level of siltation. And so that's kind of a ground floor, 3% MAD for deposition of fines. Chinook passage needs quite a bit. They're big body fish and the riffles are often wide and shallow. So 10% MAD or greater than 1 cubic meter per second. And coho fry really matched up with the steelhead in terms of how much water in the river. And really what we're hoping that you guys will take from this is it's complicated. There's a lot of competing factors, and these are ecological factors. These are not even the people factors that are competing for the same water. And so somewhere in the middle, here, the multi-value flow range, we're suggesting that somewhere between, 0.25 and 1.5 cubic meters per second is really probably, the sweet spot, 2.5 to 15%. If you will, and that would likely take care of each of these. And a really important context on this comes back to this fire hose effect, right? When we have too much water at the wrong time of the year, we're really sterilizing the river. We're getting rid of the wood and the complexity that the fish rely on. And so it's not just that we need the river to be at a certain level. We also need to manage the extremes. The peak flows and the droughts cause their own problems. And even though that might only happen for a small part of the year outside of other critical times, I think what we're seeing is the impact of droughts and the impact of high flows or peak flows is actually, leaving some scars behind each of these events. And those death by 1,000 cuts, each of those are sort of chipping away at health of the river. Just in our last few slides here before I finish up, I think one of the overall messages that I would love to leave the community with is we can see that the river shape sort of has conformed to land use, to energy, to how people over time have been interacting with the watershed. That's usual. That's not just a Koksilah thing. That's actually a global thing. But what we also know is that if we do want healthy rivers, if we do want the salmon to stay in the river, we do as a community need to figure out how to get the river back into healthier shapes and healthier forms, how to add those riparians, how to get those side channels functioning again that are no longer functioning, and really give that ecology a chance, if you will. Last couple of slides here, there are different recommendations just to sum it up for everybody that came out of the 3 studies. So when we looked at the habitat assessment or the Mesohabitat, conserving and protecting a riparian corridor is something that really stood out for us as something that is very important after these observations. Increasing the amount of healthy evolutionary river stages, which is what I just mentioned with the green dotted line, trying to transition a certain amount of the river or certain places in the river over to some healthier forms, increasing the structure and complexity overall. And both of the environmental flow needs studies said the same thing for different reasons. The desktop and the field-based each really indicated that the river needs to get up to about 5% MAD in the near term and 10% MAD in the long term through those summer low flow seasons to really give the fish, the invertebrates, the health of the river a chance, if you will. A handful of recommendations came out of this. The Mesohabitat or the habitat evaluation is really, really informative for the health of the river. And so we think it's a good idea to do that work in tributaries and headwater streams. I presented to you the flow and the fish side of environmental flows. It would be marvelous to add indigenous flows, agricultural flow needs, and community flow needs. The water is a common resource, and managing it for all of the components makes a lot of sense. Doing some more regional analysis to get at, how much is the total water, right? So maybe looking at precipitation and land use and trying to get a handle on how water is moving through the watershed, fast or slow, how to slow it down a bit. I think it's a foregone conclusion for many people that, there are serious impacts in the watershed. And so it's probably fairly easy language now to talk about needing a watershed restoration plan and needing a team that can do the watershed restoration. We haven't really touched on it here, but process-based restoration or ecological restoration is kind of working with the river to get it back into happy, healthy phases again. So those are the recommendations. And with that, I will end my presentation and invite questions after the next couple of speakers. Thank you guys very much.
Thanks so much, Jeff. We're going to take a quick 5-minute break, really just 5 minutes. So to grab a coffee or a cup of tea or whatever, and stretch your legs, and then we'll be back with Heather and Chris. And over to Heather and Chris.
Thank you. Thank you very much. This is a wonderful, wonderful experience to be standing in front of breathing human beings for an audience. The only thing I wish is you didn't have your masks on, but it truly is wonderful to have an in-person experience this evening. So let's see if I can still remember how to do this. So Chris and I are here to present this evening on the riparian piece of the project. And riparian is just a fancy word of saying stream side. So what we're going to be talking about this evening is those pieces of land, largely forest, that are occurring beside the river. I'd also like to recognize Elodie Roger, who could not be with us this evening, but she's been a very instrumental person in this project, but she's in France right now and asleep. So we're stuck with just Chris and I this evening. Okay, these little arrows there. So I don't know if Jeff is still on there. I'm going to give, hopefully not insult Jeff, and give him the forester's interpretation of what he just said. So this is again just looking at those key points from his presentation that relate to what Chris and I are going to be talking about this evening. And so far so good. So you know what I heard Jeff say is that the water table drops down, we get those summer low flows when we start to lose structure and complexity within the river system. Now, those pieces of structure are things like trees that fall into the river, those big root wads, those big rocks, And complexity is when we start losing those side channels, those nice little quiet areas for the fish to go swimming in beside the main channel. And interestingly so, all those things are related to the riparian area. Those trees and those root wads, they come from the forest beside the river. The complexity, that is when the river starts moving into that area beside the river as well. So the riparian forests are a very important part of what Jeff was talking about. And the other thing that I heard Jeff talking about is that if you can slow the water down in those really, really rainy months in the winter and the spring, then that allows aquifers to begin to recharge and start to get more water coming up into those aquifers and hopefully alleviating some of those summer droughts. And again, those involve structure and complexity. Those are all things that come from the wonderful riparian area.
Over to me. I'm equally happy to be standing in front of real people. Hi, guys. Anyway, so the first thing that we thought we should do for you is define what a riparian ecosystem is. And believe me, that wasn't easy to find a consistent definition for that. The reason being, riparian areas or streamside areas are so varied out there that it's very difficult to just pin that down to one consistent definition. However, there are commonalities in all streamside areas. So what we arrived at here is that riparian zones, first of all, they extend along the perimeter of the water, which is a stream or a lake or a pond. They go outwards to the limits of flooding. So there's actually a gradient. We always talk about riparian ecosystems, but what it really is, it's a transition zone between the aquatic and the terrestrial ecosystems. And close to the river, it's fairly wet and the water seeps into the soil and all that. And as you move away from the river, it becomes drier. But there's also flooding going on, and the limit of flooding is that second dimension that is important here. And then what actually few people realize is that the riparian area is a three-dimensional space. And it is very important, hence we put this photograph in there, that we go upward into the canopy. So we're talking a three-dimensional space, and what goes up there is immensely important for the river. So just, a lawn that goes to the side of the river, a nicely cropped lawn, is two-dimensional and really has not much of a function for the river. Is that the, okay, I got it. So again, we sampled or concerned ourselves about the first, well, it's roughly just under a third of the entire river. So the first 13.5 kilometers is our study area out of 47. I was thinking about it, isn't it Cowichan 47 as well? That could be a coincidence. They're both 40, something like that. So that's our study area here. And I think we're.
Which button did you push? Sorry.
This one.
Okay. So just ever so quickly, we had 4 main objectives as part of our project. Objective number 1 being the really important one, to assess the current riparian condition of those low fish-bearing reaches of the river. Ah, it does work. Our second objective was to assess the prevalence of culturally significant plants. And our third objective was to identify sites that require some sort of restoration to occur. And then lastly was to actually go out and do some restoration work within the Koksilah watershed. So our approach, we had 3 ways of getting the work done. The first step was a map. The map is over there on the wall. There's a segment of it here in this picture. And what happened there was for 100 meters on either side of the river, some very clever people, not me, got out and digitized where what the condition of the forest or of the riparian area was. Where is it forested? Where is it agricultural field? Where is it somebody's house? Where is it a train track? So they went through and mapped all these different types of land condition or land use. And then that was all analyzed with respect to all kinds of things like who owns the land. Is it private land or public land? Is it zoned for agriculture? Is it zoned for forestry, et cetera, et cetera, et cetera. So lots of data, lots of mapping. Then we went out in the field. Well, okay, here's the bird's eye view from the mapping exercise. What does it actually look like on the ground? Are these big trees? Are these little trees? Are there lots of invasive plants? Just all kinds of data collection to say, well, what other detail can we learn about these particular ecosystems? And then finally, getting out there with the shovel and the plants and doing some restoration work. So 3 different pieces to our approach. So again, busy table. Let's not focus in on the detail. Let's focus in more on the bolded spots. But the first thing I want to point out is that this is a table that represents some of the functions provided by these riparian ecosystems. And as part of our report, we discussed 12 different kinds of things, 12 different reasons why riparian forests are important. And for tonight's discussion, I wanted to just point out in particular the top 2. We went into the literature and we said, looked at, well, how wide do people think these riparian areas should be for all these different functions? And what we discovered is that if you want nice stable banks, research determines that we need somewhere between 9 meters and a 30-meter span of forest in order to keep that bank stable. Depends on, there's a lot of variables, slope, terrain, et cetera, but research comes up with this range of 9 to 30 meters. Now those large wood deposits, those wonderful things that fall into the river and create that structure that is so important for fish and stream health, well, their research has determined that we want somewhere between 15 and 50 meters of intact forest running alongside the stream. So those are just some ideas. But as you can see, when you look at that whole range of all the wonderful functions provided by riparian forests, you can start needing hundreds of meters when you start looking into wildlife, looking into bears and bear denning, looking into amphibians. You find you're now looking at several hundred meters of riparian forest is needed to keep those pieces of our ecosystem healthy. But tonight we're focusing on bank stabilization and the large woody debris. So 30 to 50 meters are 2 numbers just to keep on mind. So, okay, that's one thing. That's what the science says we should be protecting for riparian forests. Well, what does legislation say? And I just made this little table here. You know, Chris pointed out we did our study on 13.5 kilometers of the river. And within those 13.5 kilometers, there are so many different types of land use, so many types of land designations, that there are actually 4 different pieces of legislation that tell you how much of the riparian area you need to protect, depending on, you know, what you're zoned at. So a short section of the river, but a lot of different rules. Which rules do we follow? So what we will see in a few slides forward is that a lot of the land for our study area was zoned either agricultural or as the First Nations reserve lands. And they don't actually have a specific number that says you have to protect this much forest along the river. It's not a real firm number that's established. Instead, it's some language that's more vague about you have to leave enough to make sure you leave good fish habitat, something along those lines, whereas other pieces of legislation offer numbers. Now, and these are all maximums for where the river is the widest. As rivers get smaller and smaller and smaller, then the legislated requirements become littler and littler and littler till they finally become none. So these are maximums in this table. So this is kind of a neat little story, and we're going to step out of the Koksilah for a moment and into the Chemainus River system, because we did discover one really neat thing over there. So we just looked at functional riparian areas. How big should riparian areas be to keep the forests and the river healthy? And then we looked at what legislation says that you have to protect. Now, this is a piece of the Chemainus River that is zoned forestry. And it is an area that is partly crown land forestry and part private land forestry. And what you see is the dark green is conifer, that's your Douglas fir forest. And then what you see is the lighter green areas, that is where logging has occurred. Those are cut block boundaries. And so what you'll notice where you see a cut block is there's a thin, dark green stretch going beside the cut block between the river. And so it's a very narrow riparian area that was protected during harvesting. However, now compare to the immediately adjacent area, and this is in the municipality of North Cowichan, their community forest. And the photograph on the left is they first went out and did something called a sensitive ecosystem inventory. They went out and looked at, well, what is the ground telling us about where the riparian ecosystem is? What is the vegetation telling us? Where are we seeing the seeps? What is nature telling us in terms of where the riparian ecosystem is? And that is defined in the red color. Now, when you look at the picture next to it, that was part of our mapping project of the same stretch, and you'll see it's all green, because essentially our whole study area, our whole 100-meter study area was all embedded within that sensitive ecosystem inventory polygon. So the whole area was protected. So that was really cool. So this is showing a legislated riparian buffer that's left versus one that's best based on ecological principles. Christoph, what did we learn?
Yeah, what did we learn? We're trying to be efficient tonight, so we're going to jump right into the results now. So Heather talked already about when she mentions the sides of the river, she always mentions forest. So there's a good reason for that, because the historic riparian forests were old growth. And we know that from another study, the watershed assessment, but it was pretty well all old growth before. So there's good reasons to say forest is beside the river. Now, within that, we were looking for large structures and living and dead trees. That's what, the old growth forest would provide. And that is the structure that Jeff was referring to, that is so important to slow the river down and to refill aquifers and all that. That missing structure was always there. Now, there was this period of time where the old growth was removed, which ordinarily is done through clear-cut logging in this part of the world. So then, the clear cuts were starting to happen. And then you have to imagine now that for decades on end, there was no riparian forest. So there were no more input of structure into the river for many, many, many years. So now what we are finding now through our sort of assessment there and field work is that the current riparian forest ecosystems are mostly young second growth forests, okay? And agricultural fields in much of the study area. And those have small structures and they're mostly living trees. Part of my expertise in ecology has always been dead and dying trees, the wildlife trees at the wildlife and all that. You don't find them in these forests anymore. They're all small trees and they're living trees. So there's structure missing. What else did we learn here? Yeah, we determined that about 75% of the study area is actually recovering. Okay, so the forest is growing back, with those provisos, those caveats that I mentioned. So there's usually at least 30 meters of forest regardless of land use and ownership. So the first 30 meters, and if you put that into perspective, what Heather was talking about, the legislated buffers for riparian. So we have forests coming back there. But the large structures, and some of the large structures are redeveloped. Okay, so now we're on the West Coast here, and we're always surprised how quickly trees grow, right? And you can get sizable trees in 60, 80 years and all that. However, to get the big structures, you do need that amount of time. Then they have to die. Then the disturbance event have to get them into the river. So we're talking long periods of time here. Now, here are some data from the analysis, and what you see here is that on the First Nations reserve lands, which are located primarily they're in the lower parts and estuary parts, that I don't think we mentioned yet that we actually sampled the riparian zone from 0 to 30 meters, from 30 to 50, and then from 50 to 100. Heather mentioned that we sampled a 100-meter strip, but we had strips in there too. So what you see here is recovering forest on the First Nations reserve. In the first 30 meters, it's 90% is forested again. 30 to 50 meters is still 81, and 50 to 100 meters, 76%. Right? Now, when you go to agriculture, which accounts for 50% of the study area, you're now down to 77%, 63 and 62 respectively. And then this is interesting here, forestry. So the upper part, and here we are at Kingburn area.
Yeah.
Okay, so that's mostly the Kingburn area there. 95%, 96, 99%, is forested. Now, that is not necessarily because of intentional management or protection or so. These areas are forbiddingly steep, there's hardly any access. There will not be forestry there. So, hence you get these high numbers. But overall, it was, 75%, everything averaged. And
You can sit down now.
I can sit down now. All right. Actually,
Got to work on that a little bit. So what did we learn? This is the really key message here, and we keep repeating it in different ways, so hopefully it will sink in. So the riparian areas along the Koksilah River, they are recovering. They are not recovered, but they are on a trajectory that left to grow and left to develop the way they are. They're going to be okay. But here's the but. But legislation, that earlier slide, indicates that there is a whole bunch of room to remove a whole bunch of that recovering forest. There's really not a lot of legislation protecting that forest that is there right now. Looking at this, thinking of the slides that Chris just pointed out, 50% agricultural lands and 28% the First Nations lands, that's 78%, really doesn't have legislation saying you have to keep this many meters of your forest intact. So in this particular picture here, this is just a little snapshot of the riparian in the agricultural zone. Look at all that nice green forest. Look at all that dark green and that bright green. Look at all that forest. Almost all of that could be cleared, whether it's for more agriculture or for another vineyard or for whatever purposes. There's a lot of room within legislation to remove a lot of that wonderful recovering riparian forest.
oh, Talk to me. So now we're going into the forest. So I had the privilege of doing a lot of the field work with my First Nations buddies there. You see Colleen in the photograph here. She educated me a lot with her traditional knowledge on the value of the plants in the forest. And it became clear right away that all plants are culturally significant, but the native plants, not the European ivy or the knotweed. And quickly, cedar became a focus because I have learned since I moved to the coast that cedar is the tree of life for the Cowichan people. Huge amount of applications and embedded in the language and all that. Cedar is it when it comes to tree species. So we also found what's called CMTs, culturally modified trees in the forest, right? So that's what we zero in on. However, there are very few old cedars that we saw. Yeah, that's for sure. And few cedars are present in the new forest either. The cedar trees are having a hard time as a species overall. You know? And that's a whole different study and topic, but so we want to focus on cedar. Finally, wildlife, finally. So what did we learn about wildlife? First of all, maybe for some of you, it's not a big surprise, but when it comes to wildlife, riparian areas are it. They contain the highest wildlife species diversity of all ecosystems on the planet. That's well established, right? So there is right away for all those species that we love so much here. So the riparian areas are so important. However, riparian wildlife has been declining. And in our desktop analysis that we did before the study, it became clear that we have at least 15 vertebrate species that are now at risk. This is locally here, right, in the Koksilah. Like the western toad, the red-legged frog, cavity nesting owls. You see the little northern pygmy owl there. This little owl showed up on our property during my favorite project this winter, the project Feeder Watch, and the owl showed up. Sub-riparian species, blue listed. Okay, and elk that we know in our valleys here, they're also riparian species that are listed. So what else did we learn? And I have to say, I learned this primarily, well, from 30 years of doing wildlife ecology, but also, from the literature review. And I'd like to just stay for a couple of minutes with this slide. So what we have in our riparian zone here, in particular, is 3 keystone species. Okay, and not all of you know what a keystone species is, but you know what a keystone is in the fireplace. You take that keystone out and the fireplace just crumbles, right? The keystone species have special importance. You take a species that is a keystone species out of the ecosystem and you have this cascading effect of negative consequences, right? That's how important they are. And for our system here, the beaver, the salmon, and the cottonwood are 3 keystone species. And you see these arrows, and the thing is that they're all interrelated. If we start with the beaver builds dams and lodges and constantly eats trees, deciduous trees, right? So what does the beaver do? Jeff, as well as Heather, alluded already to the fact that the river doesn't have complexity, that we have just, a channel and all that. Okay, I'll speak faster if I can. So the beaver creates the complexity in the riparian areas. The cottonwoods are a keystone species, and the cottonwoods are, there for bank stabilization. They provide the food and the wood for the beaver and all that. The salmon benefit from the beaver. I found lots of literature that shows how important beavers are for salmon habitat. and the decaying, the dead salmon that gets moved to the land provide the nutrients for the cottonwoods, and the beaver feed on the cottonwoods. So you can see how all that is interrelated. So what did we learn? Increasing river complexity will benefit beavers and in turn salmon, other wildlife, aquifer recharge, flood control, and all that. And if you have more complexity, you have more beavers, and if you have more beavers, you have more complexity. So, you know, that's my pitch for the beavers here. So what else did we learn here, and how does this link up with Jeff's work? Well, let's come back to structure. The recovering riparian forest will someday, you know, contribute the large logs and rootwods again, if we protect those riparian forests, right? And in terms of complexity, the riparian areas must be wide enough to let the river move and let the beaver do their work. Okay, and I think it's over to you again.
Yeah. So again, another similar message between Jeff's work and ours was coming up with this whole end place of, we need a whole of watershed approach. We can't just keep looking at these little pieces here and there. And the map in the figure here is from the project of the Koksilah working group, where we came up with a draft yet to be released to the community because of COVID. Suggestion of an ecosystem-based assessment on how we can start building back integrity into the ecosystem, how we can support not only riparian ecosystems, but we have to start looking at all the parts, and not just the main stem river, but the little rivers, all those, you know, we looked at 13.5 kilometers of river, but think how many hundreds of kilometers there probably are if you add in all the small little side channels and tributaries. So what we need to do, we need to understand the whole system, the whole watershed, not just that little piece. We need to look at the upper reaches of the main stem. We need to look at those main tributaries, Glenora, Kelvin, et cetera, and all the little streams that are entering within the system. We need to look at the whole picture. And then all those restoration projects, they need to be partnerships between all the different landowners and all the different organizations doing work within the watershed. We're going to get a lot bigger bang for our buck if we start making sure all of our projects are complementing each other's projects. Another thing, if we want to start protecting more riparian areas, well, why can't we look at some sort of conservation property tax incentive? It kind of baffles me how someone gets a huge reduction in their property taxes if they log it. But if you want to conserve your property, you don't get that same type of compensation. In fact, people who right now are zoned for managed forest, if they want to decide, no, I want to conserve that forest, I want to instead put it in a conservation covenant. The one example I know of that has numbers is their property taxes would go from $600 to $6,000 a year. So to conserve is going to increase their taxes. So we need to switch it around. And just another thing, we have all these different rules, all this different legislation. Everybody has different rules about how much riparian to protect. Let's do something consistent, and let's not wait for legislation to do it. Let's even have stewardship projects that help us to get riparian protections in place. We have this water sustainability plan option coming up. We could do something really cool in there where we start having consistent riparian protection throughout that whole watershed. And just, did I skip something? I did. Uh-oh, now I have to figure out how to go back.
Maybe up there.
You know what, now there's this spinning thing going on. Okay, what the previous slide showed was some very hardworking young people working in the watershed. And it was the crews doing some riparian planting. LOD led the crew, and 2,000 shrubs and live stakes were established within the watershed. partnership between Cowichan Forestry Services. And where did our screen go now? Okay, now I'm really gonna have to wing it here. That lovely slide that was just up was just a, it's okay, there's only
Keep
2 slides
talking.
left. I don't need.
I don't know what happened.
No, it's okay, you can sit, you can sit. Was a wonderful wrap-up project as well in Bright Angel Park. 2 things going on at the same time. We had a youth crew doing riparian restoration planting, and as well we were working. Oh yes, that's right. And there was a lot of wonderful mentorship and teaching occurring with this young group, including Dave Polster and Genevieve Singleton, who are here with us this evening. So some wonderful training. You guys were focused on the live staking, I believe. Yeah. And then we also have a cedar project where we're working with Cowichan Tribes elders. It's a new project that's just starting, trying to get cedar back into the ecosystem. So the slide I'm really going to have to stretch here is the wrap up, what the residents can do. And what the residents can do is 3 things. Number 1 is protect and restore your riparian area should you be so lucky to have riparian habitat on your property. Number 2 is support any initiatives you see that come up with any discussions that have to do with getting some of those compensations or conservation compensations in place. And number 3 is supporting any whole of watershed type of projects that are coming up. So 3 things: protect your riparian, support initiatives that have conservation compensation, and number 3, support any initiatives that are looking at that whole of watershed approach. And then the final slide says questions.
He's ready.
He's ready. Hand in your questions. I'm just going to check the chat here. I'll come on.
Doesn't matter when the presentation's on, but.
So if you guys have any questions, just run them off. I've got one. Should I?
Yes, go ahead.
Okay. Okay, so I have a very complicated question for Jeff Anderson. The question is, what's a tail out? A tail out. Jeff referred to a tail out, and we're not sure what he's talking about. Like if he has a tail out or what? Can you help us, Jeff?
Absolutely. So the tail out's just downstream of the tail end. Sorry. So a tail out is a natural feature that we've all seen a lot of times. They usually come out of a pool, and it's that area in a pool where it's transitioning from the deeper depths of the pool to the shallow area right before the riffle where the rocks start to get exposed. And the important part of the tail out is that's where water is starting to compress together, and water tends to push through the gravels there. And so those are important spawning locations because of how the water moves through the riffle, and that provides the oxygen and the water movement for salmon eggs. So that's why we in river science often pay attention to tail outs, because they're a very important location.
Great, thank you. So this one would be for Heather and Chris. Is 30 to 90 meters really enough to protect the river? Assuming riparian.
I'm going to answer this one.
No, go ahead.
But the question being, is 30 or 90 meters enough? Well, my answer is going to be that politician answer of it depends. And I really refrain from giving a number that we should always protect this amount. And in the case of the community forest where I used to work, we let the land tell us like where that riparian area should be, just like the municipality of North Cowichan. In those really, really rocky canyons of the Koksilah system, I would say we're good enough with 50 meters. We still want 50 meters so a tree can fall in and fall into the river. So I wouldn't, I'd have a hard time saying anything less than 50, but in some of those areas, in the perfect world, as we get into that floodplain, it would be perhaps several hundred meters in that perfect world. But of course, now the land is developed, but that's where we need our conservation measures. But you let the land tell you, you don't fixate on numbers, is my answer.
Minimum 50.
Yeah, minimum 50.
The number is fluid.
Pardon me?
The number is fluid.
The number is fluid.
Pardon the pun. So I have a question for Jeff. One of the things that struck me in your analysis is these deep glides, right? It was pretty obvious that, 70% of the river is an unnatural habitat feature that's not particularly productive for fish. So I guess the question is, can you explain in simple terms why we've got all these deep glides if that's not a natural feature?
Sure. I think maybe the caveat for my description is absolutely I'll provide an answer, but we were looking really closely at the lower watershed, and a watershed is the sum of its parts. And so there's things happening in the upper watershed that we're not as informed on. And so, we have to realize that with my response. Sorry, I'm drawing a blank, Tom.
That's okay. So you think bedload movement, right?
I've drawn a blank on your question.
Oh, sorry. The deep glides, right? Where
Thank
do the
you.
deep glides come
Thank
from?
you.
Sorry.
Oh my gosh. Yes. So what seems to be obvious from looking at the lower Koksilah is that there's an imbalance between water and sediment in the river. And that imbalance comes at different times of the year. And I believe, and this is anecdote for me, and so please take this with a grain of salt, but I believe what we're seeing is that old historic landslides from many years gone by, not current forestry practice, but historical forest practices, have introduced huge amounts of sediment into the river. And as we have high flow, peak flow events, that sediment gets moved around. All these years later, there are these sediment wedges or slugs or big accumulations, whatever we want to call them, sort of spotted throughout the lower river. And those operate like dams. And that photo that I showed was just downstream of Bright Angel Park. And there was it presents as a gravel bar, but that gravel bar is the imbalance between sediment and water. It's a ton of sediment and not a lot of water at that time of the year. So they end up being kind of like pools that are several hundred meters long. And that's not the norm for a pool. And it's occupying a lot of river that could otherwise be a different form, a healthier function. But speculation on how the sediment's getting into the river and why the peak flows are there. So it's important for us to consider that.
I have two questions.
Oh, from,
Can I ask a question?
sorry, no way. I've got a question.
The Zoomers want to ask.
Okay, if the Zoomers have a question, you bet.
Okay, so this is for Heather and Chris, will it be difficult to get fallen trees and root wads to stay in place when the big rains come? Will the natural heavy flow during winter months continually clear cut the river?
Well, yeah, really, really good question. We have this fun little example in our neighborhood that we're getting to observe. Because sure enough, all those smaller trees, smaller things that fall into the river, yes, those storms come and they just flush them through. But we have this wonderful example in our neighborhood on the Cowichan River. We're in that big November storm. A big tree fell into the water, and the big tree with all that weight went floating along, but eventually got hung up in the middle of the river, and it has stayed there. No other storms were able to release that big tree downstream, and now we're getting to watch it at this time of year, where now it's perched on this brand new little gravel bar, and you can see it's becoming an island in the middle of the river, and it's completely changing what's happening in the river in this one location. So this is our experiment in our neighborhood to continue to watch, but we got so excited to see, yes, big things can stay in place when they're heavy enough, even in these huge storms.
Great, thanks, Heather. So here's a question that I had too, and it's for Jeff. You showed us the graphs with the changes over time on peak flows. And you said more than once that these 2-year events have the most energy, right? We've really got to look at these 2-year. So it's counterintuitive to me. So why did the 2-year flows have all that energy? You'd think it would be the like 1 in 500s. So why did these 2-year flows impart so much energy on the river channel?
Excellent question. And it's absolutely counterintuitive. And 2 ways to think about that. One is, and I think we all sort of intuitively see this in the river, that the fastest part of the river is usually in the top, in the center, or over top of that deep thing, where the river might be etched down a little bit. And where the most power is not near the stream bed, because there's so much friction between the water and the stream bed. And if we consider that concept right there, that it's that path of least resistance in the river, just that top little spot that has the least resistance, that's moving the fastest, that brings with it the most energy. And so when we're talking about a huge flood event, absolutely, there's a crazy amount of energy everywhere. But where there's not a crazy amount of energy is actually in the stream channel itself. If you were to, head on over there with your instruments and your scuba gear, you'd realize that there's, relative to the size of the flood, there's so much friction there that the water spills out and the energy is elsewhere. And so the most power in the river is that moment before the water jumps out of the river, where it's absolutely full and it's almost vibrating. It's so much it can't go. It wants to jump. It's starting to spill in certain places. And that moment right there is where it's called the formative discharge, because a lot of river form and function happens during those flow events.
Another question for you, Jeff, I think, because it's about climate change and weather events. So considering effects of climate change and predicted increase in weather events like extreme rainfall, how will the flood risk increase for the Koksilah River, and what can be done to mitigate that?
I think it's important to consider both presentations tonight for the answer here. And Heather and Chris did a really good job of sort of demonstrating the linkages between the riparian and the stream with structure and complexity. And if we're talking about floods, the flood infrastructure is riparian structure and complexity. It is floodplain availability. And so the more we squeeze the riparian and the more we squeeze the floodplain, the higher our flood risk, full stop. The other way to look at that is, as climate change does increase and precipitation increases, both in, say, frequency or the amount of rain, but also the magnitude, like those classic coastal rains that are just going hard with golf ball sized drops. Well, those increased frequency and magnitude runs the risk of moving faster, and we can call that runoff. And things that affect runoff really dramatically are road surfaces, so the road density in a watershed, or vegetation that's removed, brand new clear cuts, brand new roads, brand new shopping malls, brand new fields. And so our resilience to climate change is a healthy riverscape And a riverscape is really just another fancy word that includes the stream, the riparian, and the floodplain. And so healthy riverscapes are kind of our only resilience, or bigger bridges and bigger roads.
Okay, thank you for that. I've got a question that could go to anybody, but I'll give it to you guys because you've been sitting there for a bit. If you could define your ideal restoration project on a tributary, a small tributary, what would that be? Like if you had an opportunity to go in and do something positive as a restorative work, could you kind of generically outline what that might look like?
Describe
Or could look
our
like?
riparian restoration projects.
Yeah, we're doing it at home. Dave knows that, he was there. When we moved to our place, the 30 meters, the raw size towards the river, that entire section that we would call riparian was a dust bowl, a complete dust bowl. And it was mowed. There was no soil, it was just dirt, right? And so there was only weeds growing. And then the first thing that happened was that the Cowichan Lake and River Stewardship Society came, and they convinced us to do stewardship on the river and riparian restoration. And that was a very wonderful effort. We had the ultimate view to the river. There was no obstruction, right? And some people loved the view. And we were shown these different densities that we would tolerate. And we said, we can tolerate that. So in comes the youth corps crew, and they planted, I believe it was something of the order of 135 shrubs and trees all over the fields. Dave came and we did some live staking, along the riverbank. And that was 6-7 years ago. And oh yeah, we, the neighbors wanted to give us a welcoming gift to the neighborhood, and we said it would be really nice to have a piece of coarse woody debris in. So they did. So they took their truck and they brought this big honking piece of logs and delivered it to, anyway, so coarse woody debris. Now, after 6 years, we have an amazing amount of biomass there. We dump all biomass that we can find anywhere on the property or so into that field. We have piles of twigs and branches and all that. The other day we counted 13 snakes that were happy in that field, and so forth. So I'm giving the example from our home because you can now basically say this is what you could do on your tributaries if you have the chance and the opportunity to do that. Plant and restore the riverbank, potentially through live staking at the right time, dump biomass into the area, provide structure for the wildlife, and you have a better system.
I don't think I have anything else.
Okay, perfect. Okay, with the whole of watershed approach in mind, are there any efforts or studies to examine the uplands of our watershed and their impact on stream flows in the Koksilah? So I'm not sure who that's going to be addressed to, but maybe I can answer that in a way because it also, there's a question here to Jeff. Why did you focus on the lower river? And so for the scope and scale of this work, we focused on the salmon bearing reaches of the river. And again, that's the first step, and we've learned a lot, but it is a first step. And certainly I think as a community, holistically, we do want to take a whole of watershed approach, and Heather like spoke to that, right? So I think it's something we're working towards. And I think the water sustainability planning process that Cowichan Tribes in the province of BC are scoping right now might be one way to like start that process. So we're optimistic that, you know, this is something that might happen here in the Koksilah watershed, which I think would be great. And it would also provide perhaps the first example of a truly collaborative approach to managing water between the Crown and the First Nation, which I think would be innovative and really help to have a 7-generation approach, right, to manage things, rather than what we've done, which is always that short-term approach. I think it is, yeah.
Thank you very much, everyone, for coming.
That's nice.
Those in the room, before we go, remember the Twinned Watershed and Koksilah connections project are here. And if you're interested in volunteering or helping out with this project, it's really cool. And it's going to just add on to what Heather and Jeff and Chris have done this past year with the Twinned Watersheds. And I think it's so exciting what's going on in the watershed. So thank you all for coming and your interest. And Jill?
You're welcome. I want to, there's also a sign-up sheet here for the Koksilah Watershed Working Group for anybody who lives in the area and wants to be involved in that. I want to thank Alison and Ben, who couldn't be here tonight, for figuring out our tech today.
Yes.
You did a great job.
I also forgot to acknowledge Sherry Ayers, who was a really lead person in the Twinned Watershed Project. You know, she has worked so hard and she couldn't make it here tonight.
I think she's on the Zoom one.
Is she?
Yeah.
Okay, yay, Sherry. A lot of these people live in the Koksilah. Yeah. Okay, good night, everyone.